In this video, a couple more examples about graphing using information from derivative and second derivative, and then we will end this video with an example of just how does the second derivative test work without running through all of the motions, just getting to the crux of how the second derivative test works. So here you can see again we have some information here for graphing. Sketch the graph of a function f that satisfies the following conditions. The first one is f is smooth. In another video closely related to this one, I go over what smooth is. I will say it again here just for convenience. It means a function that is not, or I guess you could say a function that is continuous everywhere. So if it's smooth, there aren't any corners, cusps, or any discontinuities like jump, vertical asymptote, or holes in the graph. So next we have all this information here about where the original function is either increasing or decreasing based on the first derivative, or concave up or concave down based on the second derivative. So let's get that graph in here. Okay, so as said in previous video, or maybe you'll see it in a minute, I like to mark everything about the original function first. So I see f of 0 equals 10. That is simply just an x and a y value. So that is the y-intercept way up here at 0 on the graph. So anything about the original function I will be using black ink. And over here I have f of 2 being negative 6. So f of 2 way down here being negative 6. So I apologize for moving this on the slide in the middle of a video. I just realized that this graph wasn't going to be in the right place, so I needed some room up here. So the first derivative, I'm only really interested where the first derivative goes from being either positive to negative or negative to positive. So I can see that with the first derivative here, the only time we go from being negative to, let's say that like this, we have a sign change in the derivative is at the x value of 3. So since the derivative goes from negative to positive, that means the function goes from decreasing to increasing, meaning there is going to be a absolute minimum, a relative minimum at x equals 3. And so I want to put that point just a little bit below this one here, because that is going to bottom out right there. It has to be lower than the point to the left and to the right of it. So just to have some idea, this function is going to be decreasing and just kind of flatten out right there and have a horizontal asymptote, not asymptote, horizontal tangent line here. Getting my college algebra mixed in here. And then after this, it should, after this relative minimum, it should just increase from there. So let's go ahead and see what the concavity is doing here. It looks like there is some concavity changes happening here. From negative infinity to 0, the concavity is up. So I'm going to start getting some sort of idea that the graph should be like this, concave up from there to there. And if we go left to right, yes, this is still decreasing. Remember, we're decreasing all the way until we get to 3, x value 3. So that makes sense moving left to right. Let's see, the concavity does change at x equals 0. So I'm going to mark a little blue here. So you can see it goes from being up to down at 0. So that, continuing the graph, I just have to make sure this next part looks relatively concave down, something like that. And then again at 2, the graph starts being concave up again. So that means it needs to start looking like it's opening upward. But at 3, the graph has to stop decreasing. That's right here. Stop decreasing at 3, and we start increasing at 3. If the derivative is positive, the function starts increasing. So we just make sure this is still concave up and increasing. So this is what the graph should look like. Oh my goodness. Here we have another graph sketching example. So like last slide, I'm going to go ahead and bring in that coordinate plane. So one thing I want to point out here is this f is smooth on the intervals for which it is defined. So that means when we look at the vertical asymptotes here, I'm going to go ahead and put those in really quickly. So I lied. I put a lot more stuff down there. So what happens is I put all of this stuff on the graph right here. So I want to get back to what the smooth part means. That means between these two and outside of these two vertical asymptotes, the graph will not have any cusps or discontinuities, or all of the discontinuities, cusps, and corners are taken care of here. So we've got the vertical asymptotes, we've got a horizontal asymptote. The graph crosses the horizontal asymptote when the x value is negative 2.5. So I went over to negative 2.5 and plotted a point on the horizontal asymptote. There were 2 x-intercepts here and here, and there's a y-intercept here. Now something that's really going to help you graph these is noticing that there are going to be 3 intervals for our graph. There will be a graph to the left of negative 3, or less than negative 3. There will be an interval of our graph between negative 3 and 5, and there will be another piece of the graph over here when x is greater than 5. So now I want to look at things like this. These 3 intervals here will tell me how to graph just the middle piece here between negative 3 and 5. So I start at negative 3 and go to negative 2. We switch over to this part of the first derivative from negative 2 to 1, and down here from 1 to 5. Smush this all together, and that tells us whether we are increasing or decreasing between negative 3 and positive 5. So since the first derivative is negative, the first, let's see here, the first thing we should be doing is decreasing from negative 3 to negative 2. So the graph should be coming down something like this. Then at negative 2, you can see here at negative 2, it switches from being decreasing to increasing. So we should increase between here and 1. And then we should decrease from 1 to 5. So we should be doing something like this. Increase to 1, decrease to 5. Now we just have to figure out what to do with the concavity. So down here, concavity-wise, between negative 3 and 5, I just need to be looking at these 2 intervals. So between negative 3 and negative 1, second derivative is positive. That means concave up. So we are concave up here, just like that. Now, does that match up with what we had for the first derivative? First derivative says decrease between negative 3 and negative 2, check. And between negative 2 and 1, we have to increase. So as long as we can keep increasing until we get over here somewhere at 1, I'm going to plot a point, maybe that point right there. It doesn't matter where we increase to. We don't have an actual y value for our maximum. We're going to have a maximum here. But here, we move to being concave down at negative 1. So at negative 1, we switch to being concave down, which means this graph from here will open down. So let's see, so we have that one. This is where the concavity changes and it starts being concave down. And it'll stop increasing at 1. We took care of that right here. We stopped increasing at 1. Pretend that's what I did. And we started doing concave down, and decreasing from -1 and 1 to 5 respectively. So I just looked at these little intervals here to figure out what was going on the inside. And if we want to figure out what's going on over here on the left, then we can figure it out here. We should be, let's see, first derivative positive. We want to be increasing, and between -infinity and -3 down here, we're concave up. So that means this piece of the graph should look something like this, concave up and always increasing. And then lastly, from 5 to infinity, this is decreasing because the first derivative is negative, so it should be decreasing left to right. But it should also be concave up, so it should be looking something like this. So this blue graph here represents everything, and if I wanted to, I could say here we have a point of inflection, POI, and right here and right here we have relative extrema. Last slide for this video. If you've made it this far, thank you so much for watching. Let's get to it here. So, given the following information, use the second derivative test to determine if the x values represent a relative max, a relative min, or if the second derivative test fails. Now, basically, all you have to do to be successful with these exercises is the following. You just need to take these x values and substitute them into the second derivative. So why are we so interested in these x values over here? Well, these x values are given as where the first derivative equals 0. This makes them critical numbers. And if you have critical numbers, then a max or a min will occur at a critical number. So what we can do then is if we know these are critical numbers, then we should be getting maxes or mins back, right? As it's stated, see if the x values represent a relative max or relative min, and we'll get to the test fails part in just a minute. How do we do that? Why does that happen? Well, when we substitute these numbers in for x in the second derivative, so let's just say second derivative of 0 is 20 times 0 plus 1 cubed. So following the order of operations, I know 0 plus 1 is 1, 1 cubed is 1, times 20 is 20. Okay, great. We got something that's positive, and that's important. This is bigger than 0. So if the second derivative is bigger than 0, this means on this particular x value, the graph is concave up. In other words, it looks something like this. So that means this x value would represent a relative minimum at x equals 0. And that's because it is concave up at that particular point. Now, on the other hand, if you have f double prime of negative 2, and you get 20 times -2 plus 1 cubed, well, let's see, -2 plus 1 is -1. -1 to the third power is -1. This equals -20, which is less than 0, which means this is concave down, aka opening down, which means there's a relative max at x equals -2. So that was pretty easy. If it's concave up, if you get a number that's bigger than 0, concave up means you have a relative minimum. You can tell by this picture here. We have a relative minimum there. And we would have a relative maximum at x equals -2 because we got something that was negative, which made it concave down, which means there would have been a maximum there. Now in this next example, we get something that looks like this. So I use, again, these x values over here. And these x values, again, are when the first derivative equals 0, so these are all critical numbers. And since we have 3 critical numbers here, we need to check the second derivative at the 3 different values. But one problem that we come into here is that f double prime of 0 is 0. If you substitute 0 in for this particular x here, this first one, that zeroes out the entire numerator, and we're just left with 0 for everything. So this is where the test fails. We have no idea what's going to happen here. If we don't know if it's concave up or concave down, then how are we supposed to tell whether it has a max or a min? However, for these other two, I want you to substitute the value 3 and -3 in here. And I'm not so much interested in what the number you get. I just need to know whether or not you'll get something that's positive or negative when you substitute 3 in, and separately when you substitute -3 in. So give that a shot really quickly. I'll pause in talking here in a few seconds so you can pause the video and try it for yourself. Okay, hopefully you gave that a quick shot. Hopefully you got that there would be a relative maximum at x equals 3 and a relative minimum at x equals -3. So hopefully when you did this, you got something that was positive here, something that was bigger than 0, and something less than 0 here. Because if you get something that's bigger than 0, like we did up here, that was concave up, leaving you with a relative minimum, check. If you got something that was concave down, or less than 0, concave down, that means you'd have a relative max.